guys, a warm welcome to you. We are again come up with a new part, that is torque and work done on a magnetic dipole. Okay, you must have studied in your electrostatics that when the electric dipole is being placed in the field, or it means electric field, what happens over there? The similar situation we have to deal over here, that instead of electric dipole we have the magnetic dipoles, but everything remains same. And moreover also, we are not using electric field, we are using magnetic field over here. Obviously we are dealing with the magnetism. So for the detailed discussion, let's proceed. So guys, torque and work done on a magnetic dipole. Now first, what is a torque? Now if we talk about the torque, we know that torque is the force, like if we apply some force on our body and the body starts in or come in rotation. So what do we say? That body is experiencing some torque. This is what we call. Now torque on a magnetic dipole in a uniform magnetic field or a bar magnet, any dipole or a bar magnet, when we place it in a uniform magnetic field. Now guys, you must have done same thing, exactly similar thing in your electrostatics when we place a electric dipole in the uniform electric field. That means what we saw over there, what you saw over there, that that when you place a uniform or any electric dipole in a electric field, so electric force experiences by the charged particle or the negative charge particle is in the opposite direction of the electric field, but it is in the direction of electric field for the positive charge. So it is a similar kind of a thing. We can say that over here it is the same kind of a thing, that if we replace electric field by a magnetic field and negative charge by a south pole and positive charge by a north pole, so what we'll see, we'll get the exactly similar situation. So the force of magnetic, so what do we say? Instead of force QE, what we'll say, an MB force will going to act on the pole strength. That is, force of magnitude MB act opposite to each other, hence net force acting on the bar magnet due to external magnetic field is zero. So there is no translation motion of the magnet. Let's look at the figure, what exactly it is. Now if this is the direction of magnetic field and this is the magnetic bar magnet or any dipole, any magnetic dipole. So let's consider this is the bar magnet. So what we said, that north pole will going to experience force MB in the direction of the magnetic field, south pole will going to experience force MB in the opposite direction of the magnetic field. This we have already discussed. Okay, so what we can say, that this is the MB force which is acting in the direction, and this is the MB force on the south pole, it is acting in the opposite direction. And what do we say, that the angle between this line and this line, like horizontal direction and the magnetic dipole moment, is theta, and the magnetic length is 2L. Now, however, the forces are acting along different lines of action and constitute a couple. So hence the magnet will rotate and experience a torque. So we can see that these forces MB, because these has the same pole strength, so MB and MB force will going to act on the bar magnet. So therefore what we can say, it will experience, there is no translation motion because forces are equal. So instead of any translation motion, it will experience a torque and hence come in rotation. So therefore let's proceed further. So torque, what is a torque? Torque is a magnetic force perpendicular into distance, or else it is the magnetic force into perpendicular distance between the two forces. So what we can write this as, torque is equals to MB into 2L sine theta. Now if this is torque actually, tau. This is capital torque. Okay, what is 2L? Now we have considered 2L sine theta as the perpendicular distance. So both any of the definition is fine. perpendicular force into distance or force into perpendicular distance. Now if we check it out, what is there a perpendicular distance 2L sine theta? Let's look at into the figure. So this is the figure. So this is the figure. So this is MB force which is acting in this direction, MB vector, and this is the force which is acting MB vector in this direction. So MB vector. So therefore what do we say? That this should be the perpendicular distance between the two forces. So this should be the perpendicular distance. According to this figure, if I name this as O, ON should be the perpendicular distance between the two forces. So if we look at this S, if we look at this triangle A, B, O, A, B, O. If you look at this triangle A, B, O, this is angle theta. This is angle theta. M, the theta is the angle between magnetic dipole moment and the horizontal or the B vector. So what do we say? That what is ON in this figure? ON will comes out to be 2L sine theta. Hence it is the perpendicular distance. Now let's proceed further. So it is 2L sine theta. So therefore it's a perpendicular distance. Now what do we know? We know that M into 2L is M. That is magnetic dipole moment. So therefore what we can write this as? M into B into sine theta. Or else what we can write this as? We can else write this as M cross B. M vector cross B vector. So guys, consider that this is tau vector and this is M vector cross B vector. This is the thing. This is tau, actually bigger tau. So this is the magnetic field. If you look at the diagram, so this is the direction of magnetic field and this is the direction of magnetic moment, and this is the angle between the two. So if we look at this, if we take out the cross product of these two, the torque, direction of torque will comes out to be perpendicular to the plane in which B and M are lying. So therefore direction of the torque is perpendicular and into the plane containing the M vector and B vector. Okay, so let's proceed. Now work done on the magnetic dipole in a uniform field, uniform magnetic field. That means if you look at the figure, this is somewhat like, this is the situation. Consider this situation, B vector are in this direction. Now if there is a magnetic or a bar magnet, somewhat place something like this, and this is making an angle theta with the B vector. What is theta? It is the angle between the magnetic dipole moment and B vector. So what we'll see, that these are the forces which are acting on this, on the south pole opposite to the direction of field, on the north pole in the direction of the field. Now if we rotate this by a certain angle theta 2 with the horizontal axis or with respect to B vector, so what we're going to get? So we're going to get this as the orientation. So what do we say? That this is d theta and this d theta is equals to, so we have to do some work to rotate this against this. Okay, look at this thing. This has to go, or this bar magnet has to rotate in this direction, but what we have done, we have rotated in this direction. So therefore we have done some work. So we're going to see that this work will going to get further we're going to see that this work done will be act as it will store as the potential energy of this bar magnet. So what do we say? Theta 2 minus theta 1 is equals to d theta. So what do we say? The work done is equals to tau d theta. That means work done is equals to tau d theta or mb sine theta d theta. Now if we want to find out the total work done, we have to integrate this thing. That is integration mb sine theta d theta, and hence from theta 1 to theta 2 applying limits, what we are going to get? mb cos theta 1 minus cos theta 2. That is, remember this thing, this is important formula. Remember this thing, in this formula it is cos theta 1 minus theta 2, means cos of initial angle minus cos of final angle. So remember this thing. Now let's proceed. If the potential energy is arbitrarily taken 0, when the dipole is at 90 degree, then potential energy in rotating the dipole and inclining it an angle theta is minus mb cos theta. We can see this thing. We can see this thing. We have the formula of the work done is equals to mb cos theta 1 minus cos theta 2. So according to the situation, theta 1 is given to as 90 degree or theta 2 is given to as theta. So therefore what we are going to get? Minus mb cos theta. Same thing. Now let's proceed. So it is the note for us, that is the potential energy can be taken 0 arbitrarily at any position of the dipole. Like you can take any position or any reference level. So it's fine if you will take any reference level. So here they have considered the reference level to be when the magnetic dipole moment is making an angle 90 degree with the B vector. Okay. Now let's proceed towards the examples. Now in the example, what is given to us? If W is the work done in turning a magnet of magnetic moment M in the magnetic field B through 60 degree, then the work done in turning the same through 90 degree is. So let us consider that initially the magnetic moment was initially it was at an angle 0, right? So what we can say, the work done will be mb cos theta 1 minus cos theta 2. So according to this first situation, theta 1 is equals to 0 degree and theta 2 is equals to 60 degrees. So what we are going to get? We are going to get this as mb cos 0 minus cos 60. So therefore this will comes out to be mb 1 minus 1 by 2. Because cos 60 is 1 by 2, so therefore it will comes out to be mb divided by 2. This is the work done in rotation by 60 degree. You can take any other level that this will going to come out to be same. I have taken 0 as the initial level. You can take any level. So answer will comes out, definitely will comes out to be same. Now according to the second situation, my initial angle is again theta 1 is equals to 0. My final angle theta 2 is equals to 90 degrees. So therefore what I'll get by applying the formula, W nu is equals to mb cos theta 1 minus cos theta 2 and mb cos 0 minus cos 90. So therefore this will comes out to be mb. Hence if this is mb, so what we can write, and we know that W is equals to what we got, W mb divided by 2. So therefore this will comes out to be 2W. That means W nu is equals to 2W. So let's look at the options. So if we look at if we check it out the options, option B should be the correct. Now let's proceed towards the next question. So in this, a bar magnet of magnetic moment M 2.5 joule per Tesla is placed in a magnetic field of 0.2 Tesla. So what is given to us? Let's write this as 2.5 joule per Tesla and magnetic field 0.2 Tesla. Okay, the work done in turning the magnet from parallel to anti-parallel position relative to the field direction. Okay, so if the magnet is in the parallel to the field direction, that means theta, initial angle theta 1 is equals to 0 degree. Now what is the final angle? Final angle theta anti-parallel, it is 180 degree. So therefore what we are going to get? We can apply the work done is equals to mb cos theta 1 minus cos theta 2. So therefore what we are going to get? mb cos 0 minus cos 180, and we know what is cos 180, it's minus 1. So what we are going to get? mb 1 minus of minus 1. So what we are going to get? 2mb. So therefore 2mb. What is 2mb? This is work done. So let's substitute the value. M is equals to 2.5 and B is equals to 0.2. So what we're going to get? Work done is equals to 2 into 2.5 into 0.2. So therefore what we're going to get? 2 into 2, that is 0.4. That means 2 into 0.2, that is 0.4 into 2.5. That will comes out to be 1 joules. So let's check it out the options. According to this, option D should be correct.
Hopefully guys you have understood the concepts, and moreover this video or this part must have recalled your work done of the electric dipole when it is placed in electric field in electrostatics. Moreover, I'll come up with the next part, that is called the terrestrial magnetism. For that, stay tuned.